So in the last class, we have discussed about counters and we have learned about how to design ripple counter or asynchronous counters. The design was simple. For up counting in asynchronous counter, the first flip-flop, that is the LSB, is given the master clock, and the output of the first flip-flop will act as a clock to the next flip-flop, and hence it will go up to the last MSB. For down counter, instead of Q bar was fed as a clock to the next flip-flop, and we have designed also the up and down counter, which can count up and count down depending upon the external input M. Now in today's lecture, we are going to discuss about the synchronous or the parallel counters. As clear from the name, parallel counter, the clock to the all flip-flop will be synchronized with the master clock, or we can say that the clock will be common to all the flip-flops. We have to follow some design rules when we are designing synchronous counters. Now let us discuss what it is. Synchronous or parallel counter, the flip-flops are clocked at the same time by the common clock pulse. That is the major difference when we are discussing about parallel or ripple counter. In ripple counter, clock is not common, but in case of the parallel counter, clock will be common to all the flip-flops. That is the basic difference between synchronous and asynchronous counter. Now we have to follow a design procedure to design a parallel counter, and the process is as follows. In the first step, describe a general sequential circuit in terms of its basic parts and its inputs and outputs. Develop a state diagram for a given sequence, means which sequence the particular counter has to follow. Then develop a next state table for a specific counter sequence, and it says what is the present state and what will be the next state for the particular sequence. Now create flip-flop transition table. Whichever flip-flop we are using, as in case of the asynchronous counter, we are using either JK flip-flop or T flip-flop, putting the input as logic 1. But it is not true in case of the synchronous counter. Here we have to find out, or we have to finalize that which type of flip-flop we are going to use to design that particular counter. Many times in the question it will be given that you have to use this much particular flip-flop. Otherwise, for the simplicity, we use a D or JK flip-flop. We have discussed about the transition table, and the transition table says that we are known with the present state and the next state, and we have to find out whatever will be the input to that particular flip-flop. That is the transition table. So first we have to draw the state diagram, then we have to construct a present state next state table. Then with the help of the present state and the next state, we have to find out the input combinations for that particular present state next state. Now use K-map to derive the logic equation. We have to solve the Boolean function with the help of the K-map, and then at the last we can implement with the desired flip-flop and some combinational logics or the logic gates. So this is how synchronous counters are designed, and it will be pretty much easier or clear when we are going to discuss it with the help of some examples. Now suppose we have to design a mode 4 synchronous up counter using JK flip-flop. And it must be clear mode 4, it will start from 0, then 0, 1, 2, 3. So these are the 4 modes. Modes means number of states. So it is a modulo 4. So we have 4 states, and that can be represented with the help of 2 bits, 0, 1, 2, 3. So first obtain the state diagram. So here is your state diagram. It will count 4 states, 0, then 1, then 2, then 3, and after 3 it will go to 0. On the right hand side, I have noted the states with the binary equivalent 0, 0, 0, 1, 1, 0, 1, 1, and after 1, 1, it will go to 0, 0. This is known as the state diagram. how the states are moved. In the next step, we have to construct present state and the next state table. So you can see whenever present state is 0, 0, the next state is 0, 1. When present state is 0, 1, next state is 1, 0. When present state is 1, 0, next state is 1, 1. And whenever present state is 1, 1, the next state will be 0, 0. In such case, if some modes are missing, then we'll use don't care conditions. Now obtain excitation table of the JK flip-flop. So we have discussed it earlier. JK flip-flop with the present state 0, next state 0. Input combination is 0, don't care. Present state 0, next state 1. Input combination is 1, don't care. For the present state, next state 1, 0. Input combination is don't care 1. And whenever both present state and the next state is 1, 1, then the input combination is don't care 0. This we have discussed when we were discussing the flip-flops, characteristic table and the excitation table. Now in the next step, here is your present state, next state table. With present state 0, 0, next state is 0, 1. Present state 0, 1, next state is 1, 0, that is 2. Present state is 1, 0, next state is 1, 1, that is 3. Present state is 1, 1, next state is 0, 0, that is 0. So we have used two flip-flops named A and B. A is your LSB, B is your MSB. So with the help of present state of B and the next state of B, it is clearly separated with different colors. So looking into present state B and the next state B, we have to find out the input combinations JB and KB using the transition table. And with this help, we can find out like present state 0, next state 0. The present state 0, next state 0, J is 0, K is don't care. So it is 0, don't care. Present state 0, next state 1. Present state 0, next state 1. Input combination is 1, don't care. 1, don't care. Present state 1, next state 1. Present state 1, next state 1. Input combination is don't care 0. So here is don't care 0. Present state 1, next state 0. So present state 1, next state 0. The input combination will be don't care 1. So don't care 1. Similarly, with the present state of A and the next state of A denoted by the red color, we have to find out the input combination JA and K with the help of the above excitation table. So you can directly look into 0, 1. So input combination is 1, don't care. 1, 0. Input combination is don't care 1. 0, 1. 1, don't care. And wherever input combination is present state, next state is 1, 0. Then the input is don't care 1. So here these are the four inputs JA, KA, JB, KB, and we have to find out the Boolean expression with the help of the K-map for the four inputs JA, KA, JB, and KB. And here it comes. Now obtained the simplified function using K-map. So JB equals to 1A when we solve with the help of K-map. KB equals to A, JA equals to 1, and KA equals to 1. So this is how the expressions are obtained with the help of the K-map. The procedure for to design any sequence or any counter will be same. Either it is up counter, down counter, up down counter, whatever it is, the process will be same. So in the next step, finally we have to draw the circuit. So we have JA equals to K equals to 1, that is your LSB, and JB equals to KB equals to QA. So here it was QA, A is the output, it is equals to QA, that is directly connected. And you can look into the diagram that clock is common to both flip-flop A and B. So this is a major difference between asynchronous and the synchronous counter, that the clock will common to all the flip-flops. Further, we can take another example. Suppose we have to design a 3-bit synchronous binary counter. Binary counter, it will follow a binary sequence using T flip-flop or JK flip-flop. As JK flip-flop is identical to T flip-flop. If J equals to K, then it will be as T flip-flop. So we'll start with the same procedure. Present state, next state. So as it is a 3-bit synchronous counter, it will start from 0 and go up to 7, or we can say it is a modulus 8 counter. So when present state is 0, next state is 1. So 0, 0, 1. Present state is 1, next state 2. Present state 2, next state 3. Present state 3, next state 4. Present state 4, next state 5. Present state 5, next state 6. Present state 6, next state 7. Present state 7, next state is 0. So it will move in a circle starting from 0, 1, 2, 3, 4, 5, 6, 7, and then after 7 it will come to 0. In the same manner, with the help of the excitation table of T flip-flop, we'll find out the input T for the present state A2 and the next state A2 plus. We'll find T of A2. Present state A1, next state A1 plus. We'll find input T for A1. Present state A0, next state A0. We'll find input combination T of A0. The process same. Write down the excitation table of T flip-flop. Look into present state and the next state of the particular flip-flop and find out the input value, what we have done in the last example. So again, we have to solve. So you can directly look into this K-map. If we are using JK flip-flop, then we have to solve 6 K-maps, and when we are using T flip-flop, we have to use only 3 K-maps. So after solving, the value comes to be TA2 is equals to A1 and A0. T of A1 equals to A0 and T of A0 equals to 1 because all inputs are 1. You can look here, the same is plotted. And we can draw the circuit diagram. So here we can find out as TA2 is A1 and A0, and TA1 can be written as A0 and TA0 because TA0 is 1. So A0 and 1 equals to A0. So here is your circuit diagram. So I have used here JK instead of T because if J and K both are shorted, then it will act as a T flip-flop. So again, you can see with the blue line, the clock is common to all the flip-flops. First, draw 3 flip-flops, A0, A1 and A2. Here A0 will be your LSB and A2 will be your MSB. Again, take another example. Suppose we have to design a 3-bit gray code counter using JK flip-flop. So you can see the in gray code only single digit changes when we move from one state to the another state. So what you have to do first, you have to draw the state diagram, and the state diagram comes here. We'll start with 0 0 0 as 0, then 0 0 1, 0 1 1, 0 1 0, 1 1 0, 1 1 1, 1 0 1, and 1 0 0, and after 1 0 0 it is equals to 0 0 0. So don't bother about its binary value because binary value will be different. We are using a 3-bit gray code counter. The sequence will be in the gray code and the number of bits required are 3. So when we are using 3-bit, that means we are using 3 JK flip-flops to design this particular gray code counter. After the state diagram, we have to find out the state, present state and the next state table. So here is your present state and the next state. You can directly look when a present state is 0 0 0, the next state is 0 0 1. You can directly look from here. This present state next state table is directly drawn with the help of the state diagram. When present state is 0 0 1, the next state is 0 1 1. So here present state is 0 0 1, next state is 0 1 1. When present state is 0 1 0, when present state is 0 1 0, so the next state is 1 1 1 1 1 0. So here the sequence will be different. because I have written here in the binary sequence and the state diagram is in the gray code. So what you have to do, you have to just write down the three input all present states starting from 000 to 111. Then with the help of the state diagram, find out what will be the value of the next state depending upon the state diagram. Now we have to find out the input combination with the help of the excitation table, and it comes here. So we are using three flip-flops. So I have put it JQ2, K2Q2, JQ1, KQ1, JQ0 and KQ0, and with the help of sorry, with the help of present state Q2 and next state Q2 plus, we'll find out JQ2 and KQ2 with the help of the excitation table. Similarly, for Q1 and Q1 plus, we'll find out JQ1 and KQ1. Look the value of Q1 and Q1 plus from the excitation table and write down the input combination. And hence, similarly, with the for the value of Q0 and Q0 plus, find out the value JQ0 and KQ0 with the help of the excitation table. In the next step, what we have to do, we have to solve the 6 K maps for different J and Ks. So in the next step, we solve for JQ0 and KQ0. So JQ0, JQ2 comes to be Q1, Q0 bar, and KQ2 is Q1 bar, Q0 bar. JQ1 is Q2 bar and Q0. KQ1 is Q2 and Q0. JQ0 is equals to Q2 XOR Q1 bar, that is Q2 XOR Q1, and KQ0 is Q2 XOR Q1. So this is how the all 6 K maps are solved. And after finding the value of Boolean expression for J's and K's, we can draw the circuit directly. So here I have put it the values that comes in the last slide. So you can draw the circuit, and again keep in mind that clock is common to all flip-flops because we are designing synchronous or parallel counters. So this is the design how it looks like to be when we are designing from step 1 to the final step. So whatever is your problem for the designing, first you have to draw a state diagram, then present state next state table, and with the help of excitation table, find out the value of the input combinations of that particular flip-flop. In many times you will be asked to design with a particular flip-flop. It will be written in the examination in the question paper that you have to design this counter with this particular flip-flop. So you have to use that particular flip-flop. If it is not given, now always for designing a counter you have to use T flip-flop. Because when you are using T flip-flop, the number of K map will be reduced as compared to the JK. Now consider another example that will be synchronous BCD counter. So BCD counter, it will start from 0 and go up to 9, and after 9 it will comes to 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and after 9 it is 0. BCD, or we can say it is a modulus 10 counter or a decade counter. So modulus is the number of states, how many number of states a particular counter is counting or following a sequence. So it is the step 1. First we have to draw the state diagram. Then we have to find out present state. So with the 4 inputs, we have total 16 combinations, and in BCD we are using only 10 combinations from 0 to 9, and the rest of the combination will be don't care. So these are the present state. These are the next states, and the next state ranging from 10, 11, 12, 13, 14, 15. I have put it the next state as don't care. We are using only 10 valid states. Now with the help of present state and the next state, we have to find out the value of J and K for different flip-flops. So looking into the value of present state of Q4 and the next state of Q4, you have to find out the value for the J4 and K4. From Q3 and Q3 plus, you have to find out J3 and K3. For Q2 and Q2 plus, we have to find out value J2 and K2. And with the help of Q1 and Q1 plus, we have to find out the value of J1 and K1. Now in the next step, we have to solve different K maps for J4, K4, J3, K3, J2, K2, and J1 and K1. So here are the K maps. J2 is, you can look into that J1 is either 1 or don't care. That means its value will be 1. When if you are solving with a K map, there will be a combination of 16 nearby ones or don't cares. Similarly for K1, it is again, it will come to 1. So rest of the 6 K map I have solved here. So J2 comes to be Q1 Q4 bar, K2 is Q1, J3 is Q1 Q2, K3 is Q1 Q2, J4 is Q1 Q2 Q3, K4 equals to Q1. So these are the values which have came after solving the K map. So the final value J1 equals to K1 equals to 1, J2 is Q1 Q4 bar, K2 is Q1, J3 is equals to K3 equals to Q1 Q2, and K4 equals to Q1. So with this, this will be an assignment for you all, that you have to design this circuit in your book. Values are here. Either you can note down or you can try to solve it with with yourself, because always there will be a question in the examination of around 12 marks to design a synchronous counter. So this is a very much important topic in the STLD. So the designs of the circuit will be as an assignment to all of you. You have to solve it with the on your notebook. The last topic of today's lecture, or the unit 2, is your up-down binary counter synchronous. We have done the same in case of the asynchronous counter, but when we are going to design with the help of synchronous synchronous process, so here will be a clock in n bit output if you are using n bit up down counter, and there will be another input ud which will decide that the counter will count up or counter will count down. So this will again be your assignment question. Then I'll help you out that how to draw the how to design this particular counter. So the process is, if ud equals to 0, count up. If ud equals to 1, then count down. So in the next slide, here we have used 3 bits. So we are designing a 3-bit up-down counter. The bits are Q2, Q1, and Q0. So here I have written the total number of input will be 4, because UD will decide it will count up or it will count down. So for the four input combination, we have total 16 combinations, and out of which out of these 16 combination, UD will be 0 for 8 and UD will be 1 for 8. So for the first 8 combination, when UD is 0, so it will count up. So whenever UD is 0 in this sequence, this is your up counter design. So 0, 1, then state 1, 2, 2 say 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8. When UD is 1, again it will count from 0 to 7, 1 to 0, 2 to 1, 3 say next state hogi 2. If present state is 4, next state is 3, present state 5, next state 4, present state 6, next state 5, present state 7, next state 6. So you redraw this total table in a single line. So put this particular table below this table, and you will get 16 combinations. And with these 16 combination, find out the value of T2, T1, and T0 if we are designing with the help of the T flip-flop. Input will be 4 whenever you are solving with the help of the K-map, that the input will be 4, that is UD, Q2, Q1, and Q0. And you have to solve 3 K maps for T2, T1 and T0. Now finish this design in your book, and whenever we are meeting in the physical class, and I'll check out the copies, whatever question I have given you as an assignment. So let's finish this lecture here, and if you have any doubt,